So yeah, welcome everybody to this reading group session on uh, Kolmogorov Arnold networks, which have been making some noise and some claims, which not everyone is completely convinced. I'm not completely convinced, and maybe you aren't either. And so today, Evelyn is going to tell us about it. So take it away.
Thank you. Thank you. I'm Evelyn. To give my background, I've been doing open source a long time. I'm not a professional mathematician, nor am I a professional machine learning engineer. I mostly just read papers, but I read a lot of them, and I think I've got a pretty decent academic level background in this. And I'm grateful for the invitation and for your help, Jenna Taipei, with the finer points of the math. Um, I read this paper first when it came out about a month ago, and I thought it sounded uh, really quite elegant in what it is trying to do. It's taking essentially a dual perspective to MLPs and could be a drop-in replacement to MLPs. But I also had pretty serious computational concerns because all of the examples that they used in this paper and the examples I have seen in other interactive explainers have been very small, and also very small with a known function that they are fitting. But I've written a presentation and presented once on it, and this will be my second read through of the paper. And I've begun to see that there are some unique features of Kolmogorov-Arnold networks, which I think have really interesting applications. And so this read through, I'm going to be focusing on the interpretability aspects, and and a little bit on the calculation aspects, namely how they get the spline fitting. But I'm great you're here to listen. With that, I shall start. Today is June 8th, 2024, and I'm presenting Kolmogorov-Arnold Networks, a paper from MIT, CIT, Northeastern, and the NSF Institute for Artificial Intelligence and Fundamental Interactions. The senior researcher on this paper is Max Tegmark. This is a paper from the 24th of May, 2024. Abstract. Inspired by the Kolmogorov-Arnold representation theorem, we propose Kolmogorov-Arnold networks as a promising alternatives to multi-layer perceptrons. While MLPs have fixed activation weights on nodes, neurons, cons have learnable activation functions on edges, weights. Cons have no linear weights at all. Every weight parameter is replaced by a univariate function parameterized as a spline. We show that this seemingly simple change makes cons outperform MLPs in terms of accuracy and interpretability on small-scale AI and science tasks. For accuracy, smaller cons can achieve comparable or better accuracy than larger MLPs in function fitting tasks. Theoretically and empirically, cons possess faster neural scaling laws than MLPs. For interpretability, cons can be intuitively visualized and can easily interact with human users. Through two examples in mathematics and physics, cons are shown to be collaborators, helping scientists rediscover mathematical and physical laws. In summary, cons are promising alternatives for MLPs, opening up opportunities for further improving today's deep learning models, which heavily rely on MLPs. MLPs in today's models represent approximately 40% of the compute budget for a model, so alternatives are always interesting because of that. The first diagram gives a very good overview. We've got on the left-hand side here the MLP, and on the right-hand side the Kolmogorov-Arnold network. They represent two different theorems. The first the MLP is a universal approximation theorem. And a con uses the Kolmogorov Arnold representation theorem. Both of these are attempting to approximate a function, and they do them in completely different ways. The formula for the universal approximation theorem is that the function on x is approximately equal to the sum from 1 equals I to the n of c of a to the sub I times the sigma of the weights times x plus a bias. So this is a linear function on the right here, and this is approximation to that. And the Kolmogorov-Arnold representation theorem, which is also a function on x, is the sum from q equals 1 to 2 plus n, 2 times n plus 1. So this is a larger range of phi, which is the function we are learning, which takes as its parameters the sum from p equals 1 to n of phi of q sub p of x times of x sub p. So they are quite different formulas. And if anyone wants to pipe in, I'll leave a moment here. Otherwise, I'll keep going.
So one first thought I have is that for neural networks or MLPs, it's an approximation. You get closer and closer to a function you want to learn. But for CANs, or at least the Kolmogorov-Arnold theorem, it says any continuous function can be exactly represented as this kind of sum. But that doesn't necessarily tell you how easy it is to find this approximation. So that's one of my first doubts about the whole CAN thing, is that yes, you can in principle find an approximation, but this might be a very nasty representation. Like you might need some very complicated functions, and even though there's some work showing that actually you don't even need to learn the inner functions, it's only the outer functions that you need to learn. It can be in principle a very complicated function that you need to learn in order for things to work. So it's not clear to me that going from this representation theorem tells you, okay, instead of representing my function exactly, I can approximate it, get as close as I want to the function I want to learn, and of course, whether I can do that efficiently.
Thank you. I agree that finding the splines to fit this function can be very difficult. One of the reasons I think this paper is interesting is I think they've found a good technique for that, and it definitely shows the physics background of this team. And I'll continue. The model of shallow of an MLP is that you have an input and outputs, and between them you have weights which connect the input to a node and the node to the output. There's a fixed activation function on the nodes, and the weights are varied for learning. So everything happens in the weights. In a con, everything happens on the edges. The nodes are only performing a sum across the edges. All of the interesting stuff happens on the learnable functions on the edges. Notice these are all extremely different. They're all smooth in this case, but some of them are almost linear approximations to a ReLU first. And so the process of using a con is to learn the functions on the edges, not the weights. The nodes just sum. But this allows for some very interesting properties. For example, if you have an input and an output, you can trace with this technique exactly the combination of functions that led to that input mapping to output. And that's a level of an explainability that an MLP just doesn't have. In an MLP, all you get are little real numbers. connected by a function that doesn't change. You just get little real numbers. These tell you the shape of the function that relates the inputs to the outputs. And that's really quite amazing. Any other questions about this? This is the core of the paper, the distinction between these two.
So I do actually have some questions about. So they claim that these models are more interpretable. So I agree that if you think of, okay, I look at the function, it tells you how I relate the input to the output. That's maybe more insightful than the weights of an MLP. But one problem, I think it was Emily who raised that in I think in off topic, that it's a dubious claim if you consider scale. Like if you imagine a real large MLP or a very large can, the problem is that it's just you have too many functions to look at, and so it's not more interpretable or less interpretable because you can't look at all of it. And I would argue even with MLPs, okay, you have a matrix, you can still look at the SVD or the PCA decomposition of your matrix, and that usually gives you some information. I think like the Style-GAN paper was all about this. Not Style, but I've seen like some papers doing that for GANs where you look at the SVD of the one of the I think the first matrix in the decoder, and that magically gives you directions for like color or orientation and stuff. So I think you can still have some interesting things just by looking at the matrices in the MLP. And so it's not necessarily super clear to me how cans would be more interpretable, at least at scale.
And I agree with you. I think that the interpretability of Conn uh, uh, is definitely at the smaller network range, on the order of this, something smaller than the standard model of physics. Because otherwise you just have too many functions in an equation that begins to not mean anything anymore. You might be able to associate a term with one of the functions, but they really get confusing very quickly. And so I fully agree with you about that. Any other questions? Continue, we've got the deep formula, which is a multi-layer. We've got an MLP for an X equals the weights of the input node times a mean for the next layer, composed with, sorry. We've got, which is composed with the weights of the second layer, and which is composed with the activation function between that and the final layer for X. And so we've got weights and activations and weights and activations, and this is most often a fully connected layer. In Conn network, we've got these learnable functions, a set across the weights, and they are composed in layers. And the nodes, all they do is sum. So that is a little bit simpler than an MLP. And so you just add another layer and things go. Note that the Conn network illustration here does not have a fully connected output layer. These go with, at least it doesn't appear to be fully connected to me. That may be just the way that I'm reading it. And I shall continue. Introduction. Multi-layer perceptrons, MLP, also known as fully connected feed-forward neural networks, are foundational building blocks of today's deep learning models. The importance of MLPs can never be overstated, since they are the default models in machine learning for approximating nonlinear functions due to their expressive power guaranteed by the universal approximation theorem. However, are MLPs the best nonlinear regressors we can build? Despite the prevalent use of MLPs, they have significant drawbacks. In transformers, for example, MLPs consume almost all non-embedding parameters and are typically less interpretable relative to attention layers without post-analysis tools. We propose a promising alternative to MLPs called Kolmogorov Arnold networks, CONS. Whereas MLPs are inspired by the universal approximation theorem, CONS are inspired by the Kolmogorov-Arnold representation theorem. Like MLPs, CONS have fully connected structures. Okay. However, MLPs place fixed activation weights on nodes, neurons. CONS place learnable activation weights on edges, weights, as illustrated in the figure we looked at. As a result, CONS have no linear weight matrices at all. Instead, each weight parameter is replaced by a learnable one-dimension function parameterized as a spline. CONS nodes simply sum incoming signals without applying any nonlinearities. One might worry that CONS are hopelessly expensive since each MLP's weight parameter becomes CONS' spline function. Fortunately, CONS usually allow much smaller computation graphs than MLPs. Unsurprisingly, the possibility of using Kolmogorov-Arnold representation theorem to build neural networks has been studied. However, most work has stuck with the original depth 2, width 2n+1 representation, and many did not have the chance to leverage more modern techniques, for example backprop, to train the networks. In reference 12, a depth 2, width 2n+1 representation was investigated, with breaking the curse of dimensionality observed both empirically and with an approximation theory given compositional structures of the function. Our contribution lies in generalizing the original Kolmogorov-Arnold representation to arbitrary widths and depths, revitalizing and contextualizing it in today's deep learning world, as well as using extensive empirical experiments to highlight its potential for AI plus science due to its accuracy and interpretability. Despite their elegant mathematical interpretation, CONS are nothing more than combinations of splines and MLPs, leveraging their respective strengths and avoiding their respective weaknesses. Splines are accurate for low-dimensional functions, easy to adjust locally, and able to switch between different resolutions. However, splines have serious cursive dimensionality problem because of their inability to exploit compositional structures. MLPs, on the other hand, suffer less from cursive dimensionality thanks to their feature learning, but are less accurate than splines in low dimensions because of their inability to optimize univariate functions. The link between MLPs using ReLU K as an activation function and splines have been established in references 17 and 18. To learn a function accurately, a model should not only learn the compositional structure, external degrees of freedom, but should also approximate well the univariate function's internal degrees of freedom. CONS are such models since they have MLPs on the outside and splines on the inside. As a result, CONS can not only learn features thanks to their external similarity to MLPs, but can also optimize these learned features to great accuracy thanks to their internal similarity to the splines. For example, given a high-dimensional function f of x1 through n, the exponential function of 1 divided by big N of the sum of I through 1 through n of sine squared for x sub I, which is equation 1.1. Splines would fail to very large n due to the curse of dimensionality. MLPs can potentially learn the generalized additive structure, but they are very inefficient for approximating the exponential and sine functions with, say, ReLU activations. In contrast, CONS can learn both compositional structure and the univariate functions quite well, hence outperforming MLPs by a large margin. And that's in figure 3.1, which I'll take a look at. Hope you don't mind me skipping around. Oh, no, I will go back to this. We'll talk about that when it comes up.
Yeah.
I will talk about figure 2-1. Yes?
Um, while we're talking about that example, um, I mean, the there's a bunch of claims that they just made here, which like okay, to learn simple functions, MLPs don't work super well. But I think the strength of MLPs is that okay, you can throw them as your problem. You don't even know the function that you look at, and I think you mentioned that over the M's. We don't know how nice the functions we're trying to learn are, and presumably they're not nice. And to me, something like the ReLU works really well because it's able to cut up your input space into small pieces and be basically like a local linear approximation. So in some sense, you could say that ReLU are like just linear splines approximation, and you're good to go. So I'm not exactly convinced by that claim that okay, neural networks have difficulty representing the exponential or the sine function. Yes, sure, but that's not the kind of function we try to learn.
Oh, I agree with you for that. Um,
Sorry, one uh, probably dumb question, but what's like it's like univariate functions like what you mentioned like splines where like it's like the nonlinear function versus like linear in the case of MLP kind of thing. Basically, like for the case of MLP, it's like the univariate function just like the matrix, just a weight multiplication plus a bias. And in the case of Kant, it's like a nonlinear function.
I'm going to take a stab at that, and I'll apologize in advance. I'm not a mathematician. Spline functions, which I think of like, for example, Bezier curves in drawing programs, have an anchor and then a control point. And so the univariate function that cons are learning is the control point for that. And you learn it by adjusting the position of that, and the function that comes out is changed according to the position of the control point. Um,
Oh,
and I'll let
so is
someone
it
else take it from there.
interesting?
That was
Is there
completely
like on?
correct.
Sorry.
No, sorry, go.
Is I think you might go into this later, but is there like only one control point and like 2 points like next to it, and that's the only thing that represents a function, kind of?
So my understanding, and again, I'll apologize because I'm not a mathematician, is that they use a grid search for the anchor point, and then they are learning the movable point. So um, they're basically only learning one point. They're assuming the anchor point and learning the control point.
I see. So it's not like backprop and stuff. Interesting. And the compositional structure is like the whole function combined with all those splines and everything, basically.
Yes, that's
Okay,
my
thank you.
understanding. Please correct me if I'm wrong about that.
So, but maybe we can go over the relevant part in the paper. But my impression is that so for a spline you have a grid, and you have a score a spline basis over that grid, and splines are like just local polynomials. So a spline is just like an approximation of your function by locally by polynomial or piecewise polynomials, and they can work well for like a bounded domain, one-dimensional for a function. Yeah, exactly the way it showed here. But if you want a better approximation, you need to refine the grid. And so what they said in the paper is that sometimes you refine the grid in this way. So basically you add more parameters on the fly if you need to, which is a bit of a problem if you want to do that dynamically during training because you need to like all of a sudden you have new parameters um, and one issue you might have there is if you allow for different like different functions on the same layer to have different grid sizes, because then you cannot like do that efficiently in parallel as you would do with MLPs. So that's one issue people might currently have, is that there's no like efficient way to evaluate these splines in parallel, at least if you allow for some generality.
Yes, thank you for mentioning that. And I agree. I have great concerns about the computational plausibility of this for anything larger than trivial toy examples. Does that answer your question about splines?
Yep, it does. Thanks a bunch.
You're welcome. I'll keep going then. Thank you so much. Let's see. Throughout this paper, we'll use extensive numerical experiments to show that cons can lead to accuracy and interpretability improvement over MLPs, at least on small-scale AI plus science tasks. The organization of the paper is above. In section 2, we introduce the con architecture and its mathematical foundation, introduce network simplification techniques to make cons interpretable, and introduce the grid extension techniques to make cons more accurate. In section 3, we show that cons are more accurate than MLPs for data fitting. Cons can beat the curse of dimensionality when there is a compositional structure in data, achieving better scaling laws than MLPs. We also demonstrate the potential of cons in PDE solving via a simple example of the Poisson equation. In section 4, we show that cons are interpretable and can be used for scientific discoveries. We also use 2 examples from mathematics, knot theory, and physics, Anderson localization, to demonstrate that cons can be helpful collaborators for scientists to rediscover math and physical laws. Section 5 summarizes related works, and Section 6 we conclude by discussing broad impacts and future directions. And there are now many implementations of this. The original one is on GitHub. Section 2, Kolmogorov Arnold networks. Multilayer perceptrons are inspired by the universal approximation theorem. We instead focus on the Kolmogorov Arnold representation theorem, which can be realized by a new type of neural network called Kolmogorov Arnold networks. We review the Kolmogorov-Arnold theorem in section 2.1 to inspire the design in section 2.2. Section 3.2.3, we provide theoretical guarantees for the expressive power of cons and their neural scaling laws, relating them to existing approximation and generalization theories in the literature. In 2.4, we propose a grid extension technique to make cons increasingly more accurate. In 2.5, we propose a simplification techniques to make them interpretable. The Kolmogorov-Arnold representation theorem in 2.1. Vladimir Arnold and Andrei Kolmogorov established that if f is a multivariate continuous function on a bounded domain, then f can be written as a finite composition of continuous functions of a single variable and the binary operation of addition. More specifically, for a smooth function in 0, 1, n in the real numbers, f of x equals the function over x1 through xn, which equals the sum from q equals 1 to q 2n plus 1 of phi sub q, for the sum from p equals 1 through n of phi q for p of q sub p of x sub p, where phi qp is in 0 to 1 in the real numbers and phi q is in the real numbers. In a sense, they showed that the only true multivariate function is addition, since every other function can be written using univariate functions and sum. One might naively consider this great news for machine learning. Learning high-dimensional functions boils down to learning a polynomial number of one-dimensional functions. However, these one-dimensional functions can be non-smooth and even fractal, so they may not be learnable in practice. Because of this pathological behavior, the Kolmogorov-Arnold representation theorem was basically sentenced to death in machine learning, regarded as theoretically sound but practically useless. However, we are more optimistic about the usefulness of Kolmogorov-Arnold theorem for machine learning. First, we need not stick to the original equation 2-1, which has only two-layer nonlinearities and a small layer of terms, 2n plus 1, in the hidden layer. We will generalize the network to arbitrary widths and depths. Secondly, most functions in science and daily life are often smooth and have sparse compositional structures, potentially facilitating smooth Kolmogorov-Arnold representations. The philosophy here is close to the mindset of physicists, who often care more about typical cases rather than worst cases. After all, our physical world and machine learning tasks must have structures to make physics and machine learning useful or generalizable at all. And yes, I agree, this is a physics paper. Con architecture.
Sorry, can
Suppose
I?
we have a supervised learning. Yes, please do.
Yeah, so if I can comment on the above paragraphs. So if you move to the top, I think they made a slight mistake when stating the theorem because they say, no, just below. Yeah, here. So they say for a smooth f, right? They say smooth f. I think that's a mistake. It's just continuous f. Because otherwise then they say non-smooth. So to clarify, a function can be continuous, like ReLU or smooth means the derivative is nice and exists everywhere. Like the function has derivatives of all order and they're continuous everywhere. Um, Smooth functions are really nice. The Kolmogorov-Arnold theorem is for continuous functions. So it should not be smooth here on the top here. It should be continuous. And as I mentioned, continuous functions can be really, really cursed, even though they're not the worst functions you could work with. Continuous functions are not can be really complicated, and so that's why they mentioned it can be non-smooth or even fractal. Um, but I agree with their argument that in practice you wouldn't expect like really pathological to have pathological functions in most of the time, most of the cases, but that it's an important precision to make. Like the decision between continuous and smooth is quite important. Like smooth functions are really, really nice to work with. Continuous functions are much less so.
That's a very important point. If the function, so if you have a continuous function but not a smooth function, can you fit it with a spline?
So
would it be relevant to say that the continuous function would be fitted by a spline?
So any continuous function you can fit with like a spline, and where here by fitting with a spline I mean you can construct for any like epsilon, positive epsilon that you choose, you can construct a spline that remains within a distance epsilon of your function. But so okay, you get closer and closer. But if it's just continuous, okay, you get closer to the function. But if say you're trying to learn something like a ReLU, where there's the derivative is exists everywhere except at one point, the zero for the ReLU. Those would be difficult to learn properly for a spline. At least as you move closer and closer, your spline is not going to be super happy about this because your spline is always going to be a smooth function and you're trying to learn a non-smooth function with it, and so you get closer and closer, but the derivative is not going to converge because it cannot. So that's one thing that not doesn't like prevent you from learning it, but I think there's also the case that sometimes you also get non-continuous functions that you might want to learn. Like let's say I'm trying to do a classification problem a classification is like a function from my input space to a finite, to a finite number of integers. So it's not continuous. But that, I mean, even for neural networks, you have that problem. So it's not especially relevant, but you can learn just simple continuous functions. But depending on some properties of functions, you know some things about how well you can approximate it to, like how many splines you will need for that.
Okay.
But it's maybe besides the point.
So that sounds very significant that they did a little bit of a sleight of hand here with the substitution of continuous for smooth.
I think it's mostly just a typo,
And
probably. Like if you look at any other paper on the Kolmogorov theorem, they say it's for continuous functions, and from the paragraph below, I think they want to say continuous f and forgot. So they meant uh, they meant to say continuous function, but they're arguing, okay, most of the times they're nicer than just continuous.
Okay. Okay. So that isn't a fatal error in this paper. Okay.
I think the smooth in
What?
the first is just a typo, and yeah.
So why do they add sparse compositional structures here?
So this is maybe not as clear even to me what they mean by this, but presumably it means like a simple representation in let's say I can decompose my function as okay f of a plus b, like I have two inputs, I can group inputs, small number of inputs together, and then they move, and so it's not a function that takes all the inputs at the same time. It's like a tree with very few children on every node. I think that's what they might mean, but I'm not exactly sure.
Okay. Thank you. That helps. Does anybody else have any questions or comments?
Yeah, I have one. Can I ask about the picture figure 2.2? I'm trying to make sense of it. Like what is it showing? It's showing for activation function, you can approximate it with you can describe it with the what's that? The splice function. And
Spline.
what?
It's a B-spline.
Yeah, okay. And what are those like distribution looking things underneath it in the x-axis?
So I took those as the position of the grid coverage for each of the functions, which this is approximating.
Oh, okay.
And notice that when they go to a finer granularity from 5 to 10, the range of the coverage here halves, and so they get a little bit more peaky.
Okay, right. So it's just like a coverage, how much it covers.
Yes.
Yeah. Okay. Yeah. Thank you.
You're welcome. Does anybody else have any questions? Thank you. I shall keep going. 2.2 Con architecture. Suppose we have a supervised learning task consisting of input-output pairs x sub I and y sub I, where we want to find f, such as y sub I is approximately equal to f of x sub I for all data points. Equation 2.1 implies that if we are done, we can find approximate univariate functions phi of q and p and psi of q. This inspires us to design a neural network which explicitly parameterizes equation 2.1. Since all functions to be learned are univariate functions, we can parameterize each one-dimensional function as a B-spline curve with learnable coefficients of local B-spline basis functions. That's figure 2.2 right we just looked at. Now we have a prototype of Con, whose computation graph is exactly specified by equation 2.1 and illustrated in the original figure 0.1b with the input dimension of n equals 2. Appearing as a two-layer neural network with activation functions placed on edges instead of nodes. Simple summation is performed on nodes, and width 2n plus 1 in the middle layer. As mentioned, such a network is known to be too simple to approximate any function arbitrarily well in practice with smooth splines. We therefore generalize our con to be wider and deeper. It is not immediately clear how to make cons deeper, since Kolmogorov Arnold representations correspond to two-layer cons. To the best of our knowledge, there is not yet a generalized version of the theorem that corresponds to deeper cons. Breakthrough occurs when we notice the analogy between multilayer perceptrons and cons. In MLPs, once we define a layer, which is composed of linear transformations and nonlinearities, we can stack more layers to make the network deeper. To build deep cons, we should first answer, what is a con layer? It turns out that a con layer with n sub n-dimensional inputs and n sub out-dimensional outputs can be defined as a matrix of one-dimensional functions, where big ball phi is the set of psi for q and p equals 1 through n sub in, and q equals 1 through n sub out. So we're looking at a function that takes an input dimension as given and an output dimension as given, where the function phi sub q and p have trainable parameters as detailed below. In the Kolmogorov-Arnold theorem, the inner functions form a con layer with n sub in equals n and n sub out equals 2n plus 1. And the outer functions form a con layer with n sub in equals 2n plus 1 and n sub out equals 1. So the Kolmogorov-Arnold representations in equation 2.1 are simply compositions of two con layers. Now it becomes clear what it means to have deeper Kolmogorov-Arnold representations. Simply stack more con layers. Any questions about this generalization? It seems quite plausible to me that this will work.
Yeah, but I do have like one comment. So above in the top of the page, I say, okay, to the best of our knowledge, there is not yet a generalized version of the theorem that corresponds to deeper cans. And this got me like really disappointed, because if there was any paper to show that the deeper cans generalize, this should be the paper. Like, to me, this felt like, why haven't you guys done that? Because they're sort of admitting that, okay, they have their architecture, but they don't show that it can in practice approximate anything. And it doesn't sound like it should be too hard. So this, like reading this line, I was a bit disappointed. Like why didn't you do that? Like it should be easy.
It's when physicists do math.
Yeah, maybe it's not.
I mean, that sounds like.
Yeah, this to me was like the one line that got me like. But anyway.
Yeah. Does anybody have any other comments? Physicists are not mathematicians.
Yeah, can I ask, why would it be easy to generalize it, or like to according to your opinion?
So my intuition about why it should be easy to generalize is because in some way you can just reduce it. like I think in some way just reducing the by composing it this way, the composition of two continuous functions is still continuous. Sorry, so that when you stack these layers, you can just think as the last layer as the outer function, and all the ones before are just compositions. So I think the proof that you do get like universal approximation or the general theorem should be simple. But then they also have to answer, okay, what does it mean? What happens when we compose? Do we learn like okay, what is the composition of two splines like this way? Okay, it's going to be a higher polynomial. So in some sense, they're factoring their polynomial. But so I think like the intuitive proof to me is simple enough that they really should have looked into it. Even if they were physicists, that's not always an excuse. Like some physicists are a bit more rigorous. Most of them are not, but yeah, to me it's it's like when you present an architecture and claim that it's like a good alternative to MLPs, the least thing you should do would be to like prove that it can at least in principle learn any like solve any problem you might want. But yeah, again, physicists might not need that to convince themselves. But hopefully that was somewhat clear.
Thank you. Does that answer your question?
Yeah, kind of. I just can't see the full picture, but yeah, it's always that that issue with math. Like you have to probably write it down for me to look at, and then I will probably understand the entire picture. But I think I get the overall intuition.
Shall I continue?
Sorry, one question. So for like a proof of the generalized, like since we know the baseline is like capable of going from, I think like representing any function, why can't we just say like for more layers we can just have this, the network can just like map like be an identity function, like mix lines of the identity function, so it can in theory like map to any continuous function like that. Actually, does that make sense? I'm not sure.
Not sure I follow.
Yeah, I have no idea.
Okay, yeah, maybe I misunderstood something. Yeah.
I'm not sure what you mean with identity function here. So
So basically what I understood from what you said was the base cans kind of like can map the inputs to like say any continuous function, and it's yet the generalized version of with like more layers is yet to be proven. But I thought like the splines can represent. I thought you can just have like a straight line be a spline, like
yeah, that's
a
true.
do without the. So am I thinking like for more layers it can be those straight lines like identity, and it can technically still represent any function. I thought, but yeah, maybe I misunderstood
No,
something.
I think your argument is correct here. In principle, you can have just all the previous layers be the identity function, and that trivially work for just the last layer. So yeah, I think that's correct.
Okay,
Uh,
so what's still lacking from the proof for the generalized thing?
I mean, I think there's most of it.
Oh, really? Okay.
In that case, what do you actually gain from having more layers, theoretically, I guess?
So I think what you gain here is that when you compose two splines, you get a much more complex spline.
Hmm. Oh yeah, that makes sense.
And it's
Or
actually
I guess are we when they say like we don't have a generalized version of the theorem, are they looking for like more detailed like convergence theorems, I guess, or something like that, or like how fast that converges to the function or something.
Maybe they mean something about like the actual number of functions you need, but they haven't elaborated on that, so we just have to guess.
Any other questions or comments? I shall continue. Let's introduce some notation. This paragraph will be a bit technical, but it's 2.2 for a concrete example. The shape of a con is represented by an integer array from n zeros through nl, equation 2.3, where ni is the number of nodes in the ith layer of the computational graph. We denote the ith neuron in the lth layer by L, I, and the activation of the L, I neuron by X sub L, I. Between layer L and layer L plus 1, there are N sub L, I think that's what that is, times N sub L plus 1 activation functions. The activation of function that connects L, I and L plus 1, J is denoted by phi of L, J, and I equals L equals 0 through L minus 1, I equals 1 through N sub L, and J equals 1 through N L plus 1. Equation 2.4. The pre-activation of phi L, J, I is simply X, L, I. The post-activation of phi L, J, I is denoted by X tilde L, J, I defined to be equal to phi LJI for XLI. The activation function of the L plus 1 J neuron is simply the sum of all incoming post-activations. X for L plus 1 J equals the sum from I equals 1 through N sub L. For X tilde LJI equals the sum from I equals 1 to N sub L of phi LJI for XLI, where J equals 1 through NL plus 1. That's equation 2.5. And they have it in matrix form in 2.6, where the matrix entries are parameterized as expected, and they are all phi L for the position I and J. Any questions about the matrix form of this? And that is all multiplied by X sub L. And this, the matrix is denoted as phi sub L. We call that the function matrix corresponding to the Lth con layer. That is, phi sub L is the function matrix corresponding to the Lth con layer. A general con network is a composition of L layers given an input vector x sub 0 in as an element of r to the n sub 0. The output of con for x equals phi L minus 1 composed with phi L minus 2 composed all the way through to phi sub 1 composed with phi sub 0 for x multiplied by x. That's equation 2.7. This is the thing they didn't prove. We can also rewrite the above equation to make it more analogous to equation 2.1, assuming output dimension ends up big L equals 1, and define f of x equals con of x. So f of x is the sum from I, L minus 1 equals 1, through n, L minus 1 of I, L minus 1, I sub L, and I, L minus 1, which is the composition of functions which are the sum over each of the prior layers. Note that n goes from L minus 2 to 2 to 1 to 0 here. And inside the function composition is always phi of the layer for I sub 1 and I at the layer, so the layer above and the current layer of x and I at 0. And so they're composing the result of this, and this, and this, and this all the way out the number of layers they have. Any questions about that? We call this quite cumbersome. In contrast, our abstraction of Conn layers and their visualizations are cleaner and intuitive. The original Kolmogorov-Arnold representation equation 2.1 corresponds to a two-layer Conn with shape n, 2n plus 1 and 1. Note that all operations are differentiable, so we can train Conns with backpropagation. That's a strong assertion to make right there. For comparison, an MLP can be written as interleaving of affine transformations W and nonlinearity sigma. An MLP for X equals the affine transformation W at L minus 1 composed with sigma, composed with the W at L minus 2, composed with sigma, composed all the way to the W sub 1, sigma, composed with sigma, composed with W sub 0 and all multiplied by X. That's equation 2.9 for the MLP. It's clear that MLPs treat linear transformations and nonlinearities separately as W and sigma, while Conns treat them all together in phi. In figure 0.1c and d, we visualize a three-layer MLP and a three-layer Conn to clarify their differences. Would you like me to go back to that illustration now? I guess I'll do that. And here, we've got weights and sigmas, which are the nonlinear fixed activation function. This is a ReLU in this example. Again, a weights, and a ReLU, and a weights. And an MLP is composing the weights and the nonlinear activation functions through the depth of the network. Conn is composing three functions, and they're summing them. That is, phi for the third layer is passed to a summation function at the nodes, with phi at the middle layer, which is summed and passed to phi at the outer layer sub 1. And all of these functions are distinct. And this matrix is the matrix of these functions. Any questions about this?
I think we can comment on just the structure here. Right, they mentioned, okay, the MLPs treat the linearity and the nonlinear separately, whereas scans don't. But the advantage of that for MLPs is that, okay, you can do the matrix multiplication, easy to do on GPU, and there's efficient kernels. Then you can do the nonlinearity, also again easy to do on GPU. So that's the big strength of MLPs, and like deep learning in general, you can do that on GPU very efficiently, which so far you cannot do efficiently on scans. So something bitter pill.
Yes. So is there something about the structure of this function which makes it inappropriate for GPUs other than we don't have the CUDA kernels for it? Is it because the nonlinear activations across the weights are dependent on each other, for example?
I think the main one
Or is it
would be if you allow the splines on the same layer to have different discretizations. That's going to be a bitch to do on GPU. If you stick them to have all the same discretization, then life might be a bit better. You still have the problem that you're computing these splines functions, which are not, I mean, they're basically polynomials. So in some way, if you fix the discretization for a single pass, okay, then you have a bunch of functions which are essentially always the same function to call, so you can maybe vectorize that easy on GPU and then do a linear combination of those. So you use that to just evaluate a single function on a vector and then basically multiply it with a matrix or just a vector. So you can reduce it in this way. But in this case, you have, okay, big vector, then a single dot product, basically. Maybe that's more efficient if you optimize it well than just matrix multiplication and then a single kernel, but the dimensions are not the same.
So I'm not a CUDA expert, but I don't see the difference in discretization as an issue on the GPU side, because you'd have different kernels for different discretizations, and you'd call them based on which one you were using. And it would get dispatched to a different block or thread in your, a different block in your GPU, and that could be processed quite well. So I don't really see that as an issue.
I think, but again, I'm also not a CUDA expert, but from what I know, the most important thing in a CUDA program is data efficiency, to move as little data at a time and you make the most of it. And here your data, it's hidden in the weights of your splines. So each spline has like a little vector that describes its weights. And so if to evaluate a spline, first you need to evaluate your spline function at every grid, grid point. That gives you a vector of values. And then to evaluate your actual spline, you take the dot product of your vector of spline weights with these activations, or spline activations, let's call them. So if you fix the discretization for all the layers to be the same, for a single layer to be the same, you only need to evaluate the spline basis functions on only all the discretization points once, and then you just basically have a matrix vector multiplication. And because you can group all these in the dot products together, that's more efficient, at least for as far as CUDA is concerned. Whereas if you had to do separately, evaluate each discretization and compute each dot product separately, it's a bit less efficient. Because it's really the ability to fuse all these dot products into a matrix multiplication that is good in this case.
Thank you. That's given me a lot of food for thought, because it may be that this is actually highly optimizable for CUDA or GPUs.
Possibly,
if it were
yes.
to be, it might be. Okay. Thank you. Shall move on. We've done that and that. That and that. And there. So implementation details. Although the Echelon layer equation 2.5 looks extremely simple, it is non-trivial to make it well optimizable. The key tricks are residual activation functions. We include a basis function b for x, similar to residual connections, such that the activation function 5x is the sum of the basis function and the spline function. Equation 210, 5x equals the weight for b times the bias for x, plus the weight for s times the spline of x. Set the basis function for x equals silu for x equals 1 divided by 1 plus e to the negative x. In most cases, spline of x is parameterized as a linear combination of b splines, such that spline of x equals the sum over I of c sub I times big B I for x, where c sub I s are trainable In principle, W sub B and W sub S are redundant, so it can be absorbed into B of X and spline of X. However, we still include these factors, which are by default trainable, to better control the overall magnitude of the activation function. Second, initialization scales. Each activation function is initialized to have W sub S equals 1 and spline X approximately equal to 0. I'm not sure if they mean 0 squared there. Note 2. This is done by drawing B-spline coefficients, C sub I, sampled from the normal distribution, a mean of 0 and variance of sigma squared. With a small sigma, typically we set sigma to 0.1. W sub B is initialized according to the Xavier initialization, which has been used to initialize linear layers in MLP. And that is a variance scaled initialization. Update of spline grids. We update each grid on the fly according to its input activations to address the issue that splines are defined on bounded regions, but activation values can evolve out of the fixed region during training. Other possibilities are that the grid is learnable with gradient descent. B, we use normalization such that the input range is fixed. We tried the normalization at first, but its performance is inferior to their current approach. So they update the grid on the fly according to its input activations to address the issue that splines are defined on bounded regions, but activation values can evolve out of the fixed region during training. That's going to be a very important optimization. Parameter count. And any questions on the optimizations here? Parameter count. For simplicity, let's assume a network 1 of depth L, 2 with layers of equal width, and 0 through NL equals big N, with each spline of order K, where usually K equals 3, on G intervals for G plus 1 grid points. Then there are in total big O, N squared, L, G plus K, sampled from big O, N squared, LG parameters. In contrast, an MLP with depth L and width N only needs big O, N squared, L parameters, which appears to be more efficient than CON. Fortunately, CONs usually require smaller N than MLPs, which not only saves parameters, but also achieves generalization, and that's shown in figure 3.1 and 3.3, and facilitates interpretability. So they're leaning on the smaller number of parameters for interpretability. We remark that for 1D problems, we can take N equals L equals 1, and the CON network in our implementation is nothing but a spline approximation. For higher dimensions, we characterize the generalization behavior of CON with the theorem below. (2.3) CON's approximation ability and scaling laws. Recall that in equation 2.1, the 2-layer width of 2n plus 1 representation may be non-smooth. However, deeper representations may bring the advantages of smoother activations. For example, the 4-variable function f of x1 through 4 equals the exponential function of sine x1 squared plus x2 squared plus sine x3 squared plus x4 squared can be smoothly represented by a 4-2-1-1 CON, which is 3-layer, but may not admit a 2-layer CON with smooth activations. To facilitate an approximation analysis, we still assume smoothness of activations, but allow the representations to be arbitrarily wide and deep, as in equation 2.7. To emphasize the dependence of our CON on the finite set of grid points, we use phi sub L for big G and phi sub Lij at big G below to represent the notation phi sub L and phi sub Lij used in equation 2.5 and 2.6. Theorem 2.1, approximation theory COT 18. Let x equals x1 through xn. Suppose that a function f of x admits a representation f equals phi L minus 1 composed with phi L minus 2 all the way composed all the way through to phi 0 times x. That's equation 214. As in equation 27, where each one of the phi Lij are k plus 1 times continuously differentiable. They bring back continuous here. Then there exists a constant big C depending on f and its representation, such that we have the following approximation bound in terms of the grid size big G. There exist kth order B-spline functions phi, L, I, and j to big G, such that for any 0 less than equal to m less than equal to k, we have the bound of the measure of here of f minus phi L minus 1 to the big G, composed with L minus 2 to the big G all the way through to phi 0 to the big G times x, norm of that for C to the m is less than equal to C times big G to the negative k minus 1 plus m. And so they're doing a grid size here based on k and m and multiplying it by a constant. And that is the value we want to find. Does that sound correct?
So I'm not sure you really care about the constant C here. It's just this is basically like the money theorem of that paper, because it says, okay, if I have a function that's k plus 1 times proof differentiable, they're basically using the well-known theory of splines approximation, where, okay, you can approximate it this well with this many, like depending on how many discretization points you have, you're guaranteed to get a nice bound on how close you get, right? That norm, if you look at what it defines, it's the distance between f and the approximation with the can, and it's the maximum over defined on the bottom. It defines the you're looking at the distance between not only f and the function, but also the derivative of f and the derivative of the function, and all the k plus 1 derivatives, and you're taking the maximum distance between these two functions. So this is a pretty good result. And C here, typically it would actually depend on f. So if you look at stuff like the spline theory of approximation, depending on how nice the function f is, you'll be able to approximate more with more or less functions. And so, yeah, that's about sorry, that's about all there is to it. But yeah, let's keep going.
Proof. By the classical 1D B-spline theory and the fact that phi Lij is continuous function can be uniformly bounded on a bounded domain, we know there exist finite grid B-spline functions phi Lij over G, such that for any 0 less than equal to m less than equal to k, the magnitude of the phi functions composed in layers between the current layer and 0 times x minus the phi layers from L all the way down to L0 times x. And one of this is grid parameterized and the other is not. Times the constant is less than equal to the constant times the grid, the negative k, negative 1 plus m, with a constant C independent of G. We fix those B-spline approximations. Therefore, we have that residue R sub L. Find it equal here to phi L minus 1 for G, composed all the way down to phi sub 0. We are in one section here composing over the grid, and in the remainder we are not composing over the grid. Notice we lose the G here. Multiplied by x minus the same function with an additional grid parameterization layer here at phi of L, and then continuing down to 0. The residue is basically the difference that is gained between this not being on the grid and this being on the grid times x. Is that correct?
Yeah, and I think they're saying the without the phi without the g is just the real, the true functions for f. I think that's what they mean here, and so it's the difference between the approximation you get for layer L and with the grid and without.
Okay. And that satisfies the magnitude of RL for a constant is less than or equal to the term that we've been using on the right-hand side, CG to the negative k, -1 plus m. And the constant is independent of g. Finally, notice that f minus that grid parameterized composition of functions all the way from L-1 through 0 times x equals the residue at L-1 plus the residue at L-2 all the way through to the residue at 0. And they know that 2.15 holds. We know that asymptotically, provided that the assumption in Theorem 2.1 holds, cons with finite grid size can approximate the function well with a residue rate independent of the dimension, hence beating cursive dimensionality. And I'll say that again because they put it in bold. Cons with a finite grid size can approximate the function well with a residue rate independent of the dimension, hence beating the cursive dimensionality. This comes naturally since we only use splines to approximate one-dimensional functions. In particular, for m equals 0, we recover the accuracy in the L infinity norm, which in turn provides a bound of root mean square error on the finite domain, which gives a scaling exponent k plus 1. Of course, the constant c is dependent on the representation, hence it will depend on the dimension. We leave the discussion of the dependence on the constant on the dimension as future work. We mark that although the Kolmogorov-Arnold theorem corresponds to a Kahn representation with shape d 2d plus 1, 1, its functions are not necessarily smooth. On the other hand, if we are able to identify a smooth representation, maybe at the cost of extra layers or making the Kahn wider than theory prescribes, then Theorem 2.1 indicates that we can beat the cursive dimensionality. This should not come as a surprise, since we can inherently learn the structure of the function and make our finite sample Kahn approximation interpretable. Does anyone want to talk about that?
Just to comment that this might be the best argument that they so far that they gave for cans. That yes, because you reduce your problem to just running 1D splines, you get better scaling in principle. Modulo maybe the dependence of the constancy on the dimension, which as far as I know is completely unexplored. So maybe this might be where the actual difficulty lies, but yeah, that remains to see.
Thank you. Does anybody else have a comment on this? I shall continue. Yes, that's a good argument for why this might be very interesting. Neural scaling laws. Comparison to other theories. Neural scaling laws are the phenomena where test loss decreases with more model parameters. That is, L is proportional to n to the negative alpha, where L is test root mean square error, n is the number of parameters, and alpha is the scaling exponent. A larger alpha promises more improvement by simply scaling up the model. Different theories have been proposed to predict alpha. Sharma and Kaplan suggest that alpha comes from data fitting on an input manifold of intrinsic dimensionality D. If the model function class is piecewise polynomial of order k equals 1 for value, then the standard approximation theory implies alpha equals k plus 1 divided by d from approximation theory. This bound suffers from the curse of dimensionality, so people have sought other bounds independent of d by leveraging compositional structures. In particular, Michaud et al. In reference 24, considered computational graphs that only involve unary, that is squared sine x, and binary plus and multiplication operations, finding alpha equals k plus 1 divided by d star, where k plus 1 divided by 2, where d star equals 2 is the maximum arity. Poggio et al. In reference 19 leveraged the idea of compositional sparsity and proved that given a function class w sub m, functions whose derivatives are continuous up to mth order, one needs n equals big O, epsilon to the negative 2 divided by m, number of parameters to achieve error epsilon, which is equivalent to alpha equals m divided by 2. Our approach, which assumes the existence of smooth Kolmogorov-Arnold representations, decomposes the high-dimensional function into several 1D functions, giving alpha equals k plus 1, where k is the piecewise polynomial order of the splines. We choose k equals 3 cubic splines, so alpha equals 4, which is the largest and best scaling exponent compared to other works. We will all show in section 3.1 that this bound alpha equals 4 can in fact be achieved empirically with cons, while previous work reported that MLPs have problems even saturating slower bounds, for example alpha equals 1, and plateau quickly. Of course, we can increase k to match the smoothness of functions, but too high a k might be too oscillatory, leading to optimization issues. Any questions about the neural scaling laws or how they get to the bound of alpha equals 4? And they're using 4 as the size where they so they're using a rather small alpha here. Larger than in other papers. Does anybody care to chime in about this?
So to unpack this a little bit, so they're saying that the higher the alpha, the better. And they're saying that MLPs typically have alpha around 1, so not amazing. And so the way they derive their alpha equals 4 here it can be achieved with cans, but so they have this whole argument about, okay, considering some function classes of functions m times continuous differentiable, there's something about this where sorry, so yeah, right above they mentioned, okay, we want sparsity, so not many operations. Basically, you don't need to combine many all the inputs at once. I think that might not work in general, because if you think of stuff like transformers, right? Why does attention work so well? Mostly it's because you consider all pairs of interactions between your tokens. So it's expensive, it's O(n) squared, but you consider all possible interactions, and it works super well. And most attempts have at sparsity, at like linear attention, or yeah, sparse interactions between your tokens, don't work as well. So that might be some maybe not evidence, but something that you make to think that for a lot of interesting problems, you really do need like dense activation, dense let's say dense dense compositional structure. You need interaction between all your terms, and you cannot really separate them. If you could separate them, maybe you wouldn't need to use complicated models in the first place.
Yes, that makes sense. I keep hoping that we will come up with a more elegant solution than compare everything with everything. And yet it's the one that seems to work the best right now. Does anybody else have any comments about alpha or the neural scaling laws here? I shall continue. Comparison between Kolmogorov-Arnold theorem and universal approximation theorem. The power of fully connected neural networks is justified by the universal approximation theorem, UAT, which states that a given function and error tolerance epsilon greater than 0, a two-layer network with k greater than n epsilon neurons can approximate the function within error epsilon. However, the universal approximation theorem guarantees no bound for how n of epsilon scales with epsilon. Indeed, it suffers from the curse of dimension, and n has been shown to grow exponentially with d in some cases. The difference between Kolmogorov-Arnold theorem and universal approximation theorem is a consequence that cons take advantage of the intrinsically low-dimensional representation of the function, while MLPs do not. In Kolmogorov-Arnold theorem, we highlight quantifying the approximation error in the compositional space. In the literature, generalization error bounds, taking into account finite samples of training data for a similar space, have been studied for regression problems. See references 25 and 26, and also specifically for MLPs with ReLU activations, reference 27. On the other hand, for general function spaces like Sokolov-Besov spaces, the nonlinear n-width theory indicates that we can never beat the curse of dimensionality, while MLPs with ReLU activations can achieve the tight rate. This fact again motivates us to consider functions of compositional structure, the much nicer functions that we encounter in practice and in science, to overcome the curse of dimensionality. Compared with MLPs, we may use a smaller architecture in practice, since we need to learn general nonlinear activation functions. See also reference 27, where the depth of the ReLU MLPs needs to reach at least log n to have the desired rate, where n is a number of samples. That is something I hadn't heard before. Indeed, we will show that cons are nicely aligned with symbolic functions, while MLPs are not. And I would agree with that. Any discussion of the comparison? Point 4, for accuracy, grid extension. In principle, a spline can be made arbitrarily accurate to a target function, as the grid can be made arbitrarily fine-grained. This good feature is inherited by cons. By contrast, MLPs do not have the notion of fine-graining. Admittedly, increasing the width and depth of MLPs can lead to improvements in performance, neural scaling laws. However, these neural scaling laws are slow, as discussed in the last section. They are also expensive to obtain because models of varying sizes are trained independently. By contrast, for cons, one can first train a con with fewer parameters and then extend it to a con with more parameters simply by making its spline grids finer, without the need to retrain the larger model from scratch. If that's true, that's pretty big. We next describe how to perform grid extension, which is basically fitting a new fine-grained spline to an old coarse-grained spline. Suppose we want to approximate a 1D function in F in a bounded region AB with B-splines of order K. A coarse-grained grid with G sub 1 intervals has grid points at T sub 0 equals A through tg sub 1 equals b, which is augmented to t minus k through t minus 1, t0 through t g sub 1 plus k. There are g sub 1 plus k b-spline basis functions, with the ith b-spline, b sub I x, being non-zero only on t sub minus k plus 1 plus I, t I plus 1, the interval over that, I equals 0 through g plus g sub 1 plus k minus 1. Then f on the coarse grid is expressed in terms of linear combinations of these b-splines basis functions. F coarse of x equals the sum from I equals 1 equals 0 through g sub 1 plus k minus 1 times c sub I, e sub I for x. Given a finer grid with g sub 2 intervals, f on the function on the fine grid is correspondingly f sub fine for x equals the sum from j equals 0 through g sub 2 plus a minus 1 times c prime sub j, b prime sub j for x. The parameters c prime sub j s can be initialized from the parameters c sub I by minimizing the distance between f fine of x to f coarse of x over some distribution of x. Here we've got equation 216 where we're defining the set of c prime sub j, which equals the argmin over the set of c prime sub j for the expectation of x sampled from p of x of the left-hand side here is j equals 0 through g sub 2 plus k minus 1, the sum over that of the grid of c prime sub j, b prime sub j x, minus the original grid, that is I equals 0 through g sub 1 plus k minus 1 over of the sum of c sub I, b sub I for x. So the left-hand side here is the fine grid, and the right-hand side is the coarse grid, and we're doing an argmin of the expectation of this squared. And this can be implemented by the least squares algorithm. We perform grid extension for all splines in a con independently. That's important. And that might break the assumption that you had was a difficulty about using this on GPU.
Yeah, exactly.
Toy example, a staircase-like loss curves. We use a toy example f of x and y equals exponent of sine x pi x plus y squared to demonstrate the effect of grid extension. In figure 2.3, top left, we show and train test root mean square error for a 251 con. The number of grid points starts at 3, increases to a higher value every 200 LBFGS steps, ending with 1,000 grid points. It's clear that every time fine grading happens, the training loss drops faster than before, except for the finest grid with 1,000 points, where optimization ceases to work, probably due to bad loss landscapes. However, the test losses first go down and then go up, display a U-shape due to the bias variance trade-off, underfitting versus overfitting. We conjecture that the optimal test loss is achieved at the interpolation threshold when the number of parameters matches the number of data points. Since our training samples are 1,000 and the total parameters of a 251 con is 15 times g, g is the number of grid intervals, we typically expect the interpolation threshold to be g equals 1,000 divided by 15, or approximately 67, which roughly agrees with our experimentally observed value of g approximately equal to 50. Let's take a look at 2.3. So we're fitting f of x equals exp sine pi x plus y squared. In the upper left, we have a con. The left column is con of 251. The right column is con of 211. In both cases, we have a similar y-axis and a similar x-axis. In the case of the Con 251, the orange line is the test and the blue line is train. Notice that after about 1600 steps or grid size of 1000, they get an instability in both the test and the train sound. Otherwise, as the grid size increases, the root mean square error is monotonically decreasing until the interpolation threshold, which is approximately equal to grid 50 at about step 900. The test loss matches pretty closely the train loss until about step 600, and then they slightly diverge. And at about step 900, they're not matching at all. On the right-hand side, we have a con with a network of 211 that's much smaller. Note that the function is much noisier here, though again, both the test and the train match very closely through to the interpolation threshold at approximately 1100 step or a grid size of 100. And again, they notice this discontinuity at about grid 1000 or a step 1600, which is similar to what they noticed with a larger network. In both cases, the Y-scale is the same, so these are directly comparable. The interpolation threshold in the smaller network is many more steps out, approximately 20% higher. On the bottom row, we have a test loss on the Y. These two Y's are not the same, and the X's are not the same either, so these are not directly comparable diagrams. The one on the right, which corresponds to the con of 251, blue line is con 211, the black line is con 251, and the pale blue line is con 211 with a, and they're all across different functions. This line is square root mean of squared. This one is square root mean of squared. And this one, the light one, is square root median of squared. They're different functions. We also have different grid sizes. We've got a grid 2 here with the black dotted line and a grid to the -3 of the blue dotted line. And very pale, there's a grid to the 4 of the pale blue dotted line. In case of Y, test loss decreases until a pivot point, I'll call that, where the smaller grid stops performing well, but with a coarser grid, with a finer grid, it continues to improve much longer. Now on the right-hand side, we've got the black line is a con 251, the blue one is a con 211. So this is coarser and this is coarser, this is finer. The training time in seconds goes up with the finer grid, which is expected. And again, there is a U-shaped function where there's a discontinuity at approximately 10 to the 2.75 grid size. And so they get slower as the grid size gets smaller. Any questions about these diagrams?
So again, a comment, but more on the so what they were saying about the grid size. So one major disadvantage I can think of doing this is because you're approximating a function with spline on a grid. If you take a finer grid, you can basically, by definition, using splines for this means you will overfit on your data if you take a small enough grid size. By definition, because the spline only fits your data locally. So if you take a very fine discretization, then it can trivially just like overfit on the data. So that might be an important argument against scan, that it's not sure how well they will generalize. And so, of course, if you have a model that's overfit, um, then there's not much to say about interpretability. If it's super overfit, then you like ideally you want to interpret interpretability on a model that has generalized, because you think it has learned some like general features that might be interesting. But if it's overfit, then there's no like actual generalized features. So that's a potentially, I think, a big point against scans. At least if you use splines, you could use other function approximation techniques, but splines, I think, would by default overfit.
That's an excellent point. And these diagrams would suggest to me that they aren't generalizing. Test set isn't continuing down to a low loss after the interpolation threshold.
Yeah, it's also a shame that they don't investigate exactly what happens at this point. They don't say, oh, probably it's overfitting or numerically unstable, but we haven't checked. That's unfortunate that they haven't checked.
I wonder if anybody else has investigated that point yet. This paper has made quite a splash, and a lot of people are looking at these right now. I haven't seen anybody talk about this particular issue yet, though. And that's an excellent point. Thank you for mentioning it. Does anybody else have any questions or comments about this? Shall continue. Small cons generalize better. Is this the best test performance we can achieve? Notice that the synthetic task can be represented exactly by a 2-1-1 con, so we train a 2-1-1 con and present the training dynamics in figure 2-3 top right. Interestingly, it can achieve even lower test losses than the 2-5-1 con, with clearer case structures, and the interpolation threshold is delayed to a larger grid size as a result of fewer parameters. This highlights the subtlety of choosing con architectures. If we do not know the problem structure, how do we determine the minimum con shape? In section 2.5, we will propose a method to auto-discover such minimal con architecture via regularization and pruning. Scaling laws, comparison with theory. We are also interested in how the test loss decreases as the number of grid parameters increases. In figure 2.3, bottom left, a 2-1-1 con scales roughly as test root mean square error proportional to g to the negative 3. However, according to theorem 2.1, we would expect test root mean square proportional to g to the negative 4. We found that the errors across samples are not uniform. This is probably attributed to boundary effects, reference 24. In fact, there are fewer samples that have significantly larger errors than others, making the overall scaling slow down. If we plot the square root of the median, not the mean of the squared losses, we get a scaling closer to g to the negative 4. Despite this suboptimality, probably due to optimization, cons still have much better scaling laws than MLPs for data fitting in figure 3.1 and PDE solving in figure 3.3. In addition, the training time scales favorably with the number of grid points G shown in figure 2.3 bottom right. And they say when G equals 1000, training becomes significantly slower, which is specific to the use of LBFGS optimizer with line search. We conjecture that the loss landscape becomes bad for G equals 1000, so line search with trying to find an optimal step size within the maximal iterations without really stopping. That's plausible. External versus internal degrees of freedom. A new concept that Kahn highlights is the distinction between external versus internal degrees of freedom parameters. The computational graph of how nodes are connected represents external degrees of freedom. DOFs, while the grid points inside an activation function are internal degrees of freedom. Cons benefit from the fact that they have both external degrees of freedom and internal degrees of freedom. External degrees of freedom that MLPs also have, but splines do not, are responsible for learning compositional structures of multiple variables. Internal degrees of freedom that splines also have, but MLPs do not, are responsible for learning univariate functions. 2.5 for interpretability, simplifying cons and making them interactive. One loose end from the last subsection is that we do not know how to choose the con shape that best matches the structure of a dataset. For example, if we know the dataset is generated via the symbolic formula f of x and y equals the exponent of sine pi times x plus y squared, then we know a 2-1-1 con is able to express this function. However, in practice, we do not know that information a priori, so it would be nice to have approaches to determine this shape automatically. The idea is to start from a large enough con and train it with sparsity, regularization, followed by pruning. We will show that these pruned cons are much more interpretable than non-pruned ones. To make cons maximally interpretable, we propose a few simplification techniques in section 251 and an example of how users can interact with cons to make them more interpretable in section 252. 251 Simplification techniques. First, sparsification. For MLPs, L1 regularization of linear weights is used to favor sparsity. Cons can adopt this high-level idea, but need two modifications. First, there is no linear weight in cons. Linear weights are replaced by learnable activation functions, so we should define the L1 norm of these activation functions. Second, we find L1 to be insufficient for sparsification of cons. Instead, an additional entropy regularization is necessary, and they discuss that in Appendix C. Any comment about those two sparsification modifications? Continuing. We define the L1 norm of an activation function phi to be its average magnitude over its n sub p inputs. That is, the magnitude of phi n sub 1 is defined to be equal to 1 divided by n sub p times the sum from s equals 1 to n sub p of the magnitude of phi x to the s, average magnitude. Then for the con layer of phi with n sub in inputs and n sub out outputs, we define the L1 norm of phi to be the sum of L1 norms of all activation functions. That is, the magnitude of phi sub 1 is defined to be equal as the sum from I equals 1 through n sub in times the sum from j equals 1 to n sub out for the magnitude of phi ij sub 1. In addition, we define the entropy of phi to be, entropy of phi is defined to be equal to the negative sum I to n in, j to n out, of the magnitude of phi ij for 1, divided by phi magnitude for 1 times the log of the magnitude of phi ij at 1 divided by phi at 1. This is a few sums, an average of instance over general, and then the log of instance over general. That's equation 219. Entropy, yeah. The total training objective, L subtotal, is the prediction loss, L subpred, plus L1 and entropy regularization of all con layers. The loss total equals the loss predicted plus lambda times mu sub 1 over L. L0 sum across to L minus 1 of the magnitude of phi L sub 1 plus the second mu or L0 through L minus 1 of the entropy over phi, which is equation 2,2. And this is the total loss, which is the predicted loss, plus the L1 and entropy regularization. mu1 and mu2 are relative magnitudes, usually set to mu1 equals mu2 equals 1, and lambda controls overall regularization magnitude. This feels like a pretty plausible a training objective. Don't see anything unusual there. And now we get to another interesting diagram section, figure 2.4, which is how to do the symbolic regression with Kahn. They start with a known function input into the network, which is summed, and learnable activation functions. Sparsification happens in step 1, where they are only taking a very small number of paths through the graph, and then they prune down to just those paths. So they go from a full Kahn network down to just the ones that appear to affect the outputs, and then they use only those elements in the graph. They on step 3a, they set the sign, so they already know by sign the sign function, which they already know they're fitting. And so this is a little bit of, we know the answer, therefore we're using the answer to find a good way to solve the problem. They set the sign, which is that. Set the squared, which is that. And then they set the exponential. Then they train the Appling parameters to reach the machine precision, which gets them back to an output symbolic formula. This almost feels a little bit like cheating here, because they know the function they're attempting to fit at the beginning. In machine learning, that is rarely the case. And the pruning step, I believe, is where most of the heavy lifting is happening here, and they don't really explain that very well in this diagram.
Yeah, there's also another issue for me, which is basically step 3a, 3b, and 3c. They say, okay, they say, okay, in 3a, we look at the function on the bottom left. It looks a bit like a sine wave, so let's replace it with a sine wave. And then they do, okay, the other one looks a bit like a square, so let's replace it with a square, and the other one looks like an exponential, so let's replace it with an exponential. Cool, but how do I know that the function I get in my can will look like any function I know? So that's a bit arbitrary,
Exactly.
and if you don't know what you're looking for, then good luck. Like in practice, this type of process you could do with like actual symbolic regression, which so symbolic regression, you can also use that for neural networks if you know that they've learned like some niceness functions, and then they'll try and find some analytical expression that matches the output of your function. So it might be interesting to compare like their methods and actual symbolic regression methods.
Yes. So I had less problem with the final 3 steps here than I did with the pruning step. And that's because you could pattern match towards something that appeared to be close to that. And it may not be correct, but most of our common mathematical functions have very distinct shapes. And so it's unlikely that they're going to confuse a sine with an exponential.
Sure, but
this pruning,
what guarantees me that the function
step,
that I get after that pruning will look like anything I know?
nothing.
Exactly.
Or even that the pruning will find anything.
That too.
And this might be a good time to go over to the explainer I was going to share, because that might help a bit. And this is an explainer from canvas.deeptech.verse. And in this particular interactive, they are using the functions which they are splining to as inputs to the problem they're solving. So they're bootstrapping the splines with these functions. And I'll take a simple example here where they're trying to do a classification of two interleaving half circles. They've got a 90% ratio of training to test. And we run this for 10 steps with a LBFGS training option. And notice that the functions very quickly match to something which is going to separate these two and something which really doesn't. And then we've got the training test loss, and they get an F1 score of 1 and a testing accuracy of 1, which is not unreasonable for a function which is this simple. They could select many more input functions and do it again. I will reset and do it again. And that spends a little bit more time puzzling, but again settled on exactly the same two spline approximations. I'll do the same with the smooth function. Take off all of these inputs, let it find the splines. Again, we'll go and do 10 steps. I'll take a little time to look at the output training loss on this one. It's a little interesting in this one. Training loss decreases pretty rapidly, and they come up with what I consider to be a pretty interpretable function. The root means the loss is pretty good, the error is pretty good. We can do the auto symbolic. Okay. On this, let's say stop, and then we train this again. And again, we come up with splines which approximately match what we would expect for that. This one isn't giving us the equation as the output. I have seen other tools that do. So this is useful for kind of developing a little bit more of an intuition about this. This is a tiny con network. We can do a larger one for a more complicated discontinuous function. And I'll generate the data here. The auto symbolic. Now that this one, even for a small network, is coming up with a reasonable approximation, a decent law error, and a decent R squared pretty quickly, though I can't say that I understand what these mean in this case. Fitting this function, which is linearly separable in one plane, but not in any other plane, which would be this. And the other two are sort of relevant to this, but I really wouldn't know how to begin to assume this is interpretable. I'll try the auto symbolic here. I'll start. This isn't doing anything yet. Anyway, this isn't working. Does this make sense for anybody? It's a good tool to play with a little bit. And I apologize, it's been 2 hours and I'm running out of steam a little bit.
Yeah, I do notice it's also been 2 hours. So yeah, this tool is interesting and all. One thing like I'm puzzled about, and they haven't mention it at all is that they use LBFGS. So for those who don't know, LBFGS is an optimization algorithm, a bit like Newton method. It's an approximation of Newton method. It's like Newton method. If you don't know how to compute the Hessian of your map, you use LBFGS and it's going to approximate the Hessian. So it's in practice a second order method. So of course, on neural networks, you can't afford that. So it's interesting that they use LBFGS for this. This might be another limitation. Like if you need second order methods, um, your method is not going to scale super well because you need a lot of memory for that. But that side, okay, in these simple examples, they find interpretable functions that look interpretable, but there are functions that are not interpretable, and even in physics and so on, you have like, let's say I want a model that wants to look at the integral of the Gaussian function, so e to the minus x squared. We know that there's no nice analytic expression for this integral. We don't have it. Like there's no simple way to express it, except as an integral. So, and even in physics, you have a bunch of these like very nasty functions that can only be defined as like an integral or a series, and we know that there's no way to express it analytically in a simple closed form. So these might be like functions that might not be interpretable, and then okay, what do you do? Also, this sort of like you have to assume that come up with a bank of functions that you consider interpretable and sort of try to fit your data to it. This, to me, would be some kind of bias. Maybe it's a good bias. Maybe you can actually find like a good approximation. It might be completely false. It might be that you get a function that sort of matches, but it's not even correct. So that's depends on what you find. And okay, in these examples, they have examples from physics and math. So okay, in this sense, we know that they have simple representations, but what is there to tell me that MNIST has this kind of nice, simple interpretable function? If I try and manage to train an MNIST model with something like this, and it tells me, okay, it looks like a square function here, a sinus function here. How how do I even begin to interpret that? So that's not clear though to me. How you would be able to interpret these functions for an actual like problem like MNIST or like or just image models or complicated models where we don't have a proper idea of the, let's say, underlying data manifold, if we want to put some assumptions.
So I will mention that I did think that these would be very helpful in mechanistic interpretability situations, manufacturing operations, robotics, where you have a mechanism where you don't necessarily have a good model of them, but you know that the model is going to correspond to physics. I do agree that these are not going to be very useful for very high-dimensional symbolic or human symbolic problems like MNIST or language models. But I think these might be very useful in things like protein folding and robotics.
Yeah, that's a good point. I think they're trying to like orient themselves as that. Okay, for scientific machine learning. Then I think they would also have to answer the okay, why use cans instead of physics-informed machine learning or physics-informed neural networks, which is pretty successful so far. There's been like a couple of really interesting applications of that, even for like fluid mechanics, where some I think mostly physicists used a neural network to find initial conditions for a fluid mechanics problem to show that it existed. And there's already a large literature on models that using neural networks to do science, where you yourself, the scientist, encode the constraints of physics into your model, and so then you have a model that you know most of the physical part, but this part you don't know exactly, so you ask a neural network to train it, and it works reasonably well. And often you can even maybe get some interpretability out of it if it's simple enough, but most of the time it's also just I'm trying to think of a specific example here, but well, there's two things. One is that you have a lot of these techniques to take your trained neural network and extract an interpretable representation exactly the same way that they do here, or mostly the same way. So again, it's a matter of scale and then whether it works. The other big thing is, especially for fluid mechanics and PDEs, is that you can train a neural network to compute the solution of a PDE, and it's going to be often just much faster than if you'd done it the traditional numerical way. And so here the gain is just speed. You can now solve your problem a lot faster, and that's why you see now like companies like NVIDIA going hard on machine learning for climate models, because there's a real argument that because you can now solve PDEs from climate much faster, and you can still scale them a lot more, um, you can tackle problems like climate change much easier, because simulations that would previously take you like weeks or days, now you can do like make them 100 times faster, maybe 1,000 times faster, and you can do them a lot more. So here there's a real like they do need to answer, okay, how do they compete well with neural networks for science in this case?
I think this technique has some potential for further exploration. I also am not convinced that it is computationally affordable or adding a lot on the interpretability side. More research is needed, as is always the case in this field. Thank you so much for hosting me. This was fabulous. And thank you, Gen X, for helping so much with the math.
You're welcome. Yeah, I think we can wrap it up here. Unless someone else has questions. Yeah, I guess not. It has been 2 hours, so yeah. Thank you very much, and also for the 2 hours. I'm not sure I could have done so. Um, so yeah, I think I have the recording. If it's scuffed, maybe either Evelyn or I think maybe Bone Amputee has the recording. So to come up soon. Yeah, I've gone out. I'm going out of this meeting maybe a bit more optimistic on cans. I'm still a bit skeptical, but yeah, I have some interesting ideas about them. But maybe I'll share them or not. I don't know. So yeah, thank you again, Evelyn. And yeah, the next one I don't know when it will be, but it will be at some point in the future. So yeah, thanks everyone, and have a good one.